Welcome to Lesson 6 of my Basic Electrical series. In this video, we're going to talk about motors. Now, in the past, we have included this in sections outside of Basic Electrical, but I'm changing that because more and more motors are part of everyday life in the HVAC industry. You're not going to work on a single system that doesn't have a motor connected someplace to it. Having motors in the basic electrical will make it easier to master the specialty material found in future modules. Motors consist of a stationary part called the stator that surrounds a rotating part called the rotor. One or more windings are mounted on the stator. There are no windings usually on the rotor for AC motors. Here's a breakdown of the motor parts itself. If you break a motor open, you're going to find the housing. You're going to find a base or some way to stabilize it. Inside, you're going to see windings on the stator because it stays still, sort of stator stays. Rotor is going to be a part, pretty much little magnets. There's going to be a shaft connection, and then you'll have bolts to hold it together. Sometimes there's a cooling fan in here as well. And then you'll have what's called an end bell or an end cap. Shaft will stick out on one or both sides depending on the motor you're talking about. Lots of little bolts, lots of little pieces. Don't take them apart unless you absolutely have to. Most motors we do not service in the field. The rotor, or the center part of the motor, is not connected to any external source of voltage. When the winding on the stator is powered, it generates a magnetic field. As the AC changes from a positive to a negative, this magnetic field will rotate. Okay, so when we take a look at a magnetic field, okay, we put a magnet in the center. Like poles of a magnet repel each other. So if I have a north and north together and a south to south together on a magnet that can pivot, it's going to try to push away from each other. Okay, so it's going to rotate. And it's going to try to always get to the point where north and south are together. Okay, because unlike poles attract each other. Well, you might ask, why does the motor keep rotating? Bottom line is, alternating current in a coil, we alternate the poles. Okay, so as the magnetic field of the stator winding changes from a positive to negative, it chases the rotor as the poles on the rotor are positive and negative. So as the magnetic field keeps reversing 60 times a second, it reverses north and south, and it continues to push that rotor around. This constant change in the magnetic field will keep the motor running. The problem comes up when you're trying to start a motor. If the magnets are lined up evenly between the poles, the motor would not start. This is the purpose of a start winding, or sometimes in some motors, some little copper plating we put in there. We'll talk about that in a minute. So we have a stator, we have our run winding, and we have a start winding. The start winding is an additional winding in a single-phase motor that allows the motor to start when the poles of the stator and rotor are not in the correct position. The current applied to the start winding is slightly out of phase with the current applied to the run winding. The run winding is the winding on the stator that allows the motor to continue to operate. The run winding gets constant voltage until the motor is shut off. The start winding, on the other hand, may not always have constant voltage, or sometimes does, but it's still out of phase. We'll talk about that in one of our motor types. The shaded pole motor is the simplest motor. Okay, it's the lowest cost one as well, and you'll find it in most like room fans and stuff like that. It has one winding surrounding a laminated core. It uses a shaded pole to determine its rotation. The shaded pole motor consists of a squirrel cage rotor, an iron core, and two or more rings poles with a coil and small copper inserts. The insert slows the buildup of the magnetic field just enough to cause rotation towards the magnetic field. The action provides for induced magnetism into the rotor. The rotor will then turn if it's attracted by the magnetism. Movement of the rotor will continue as long as there is change of polarity of the poles and the rotor. If the motor stalls or if the bearings freeze, in shaded pole motors, they will usually not burn out. When the motor is in a locked condition, the winding will actually draw very little current. The direction of the shaded pole motor is always towards the shaded pole. Shaded pole motors can be made multiple speed by inserting additional voltage taps. Shaded pole motors are low in cost but have a very low starting torque and a very low power factor, very small loads. This is an example of a shaded pole. Okay, we have our wiring diagram up here. Basically, it's just a coil. Okay, and if you want to take a look and see how it's sort of designed, we have our L1 that continues to wrap around the stator, okay, and there's a copper band. So the movement of the rotor is always towards the copper. Okay, that's the shaded pole. So it's always going to go towards the shaded pole. So in this case, looking at it from the end we're looking at, this motor has a clockwise rotation. Shaded pole motors are built for very small sizes and are used for light duty in small appliances. In refrigeration, shaded pole motors are very frequently used for evaporator fan motors. Our next motor is a split phase motor. Split phase motors are also called induction start, induction run motors. These motors generally use a current relay or centrifugal switch to remove the start winding from the circuit. The start windings work on the phase shift principle. In other words, they're out of phase. The voltage from the start winding to the run winding is 10 degrees out of phase. Okay, remember our sine wave that looked something like this. Okay, that's one cycle with 0 in the center. If that's our run winding phase, our start winding is 10 degrees out of phase. So in other words, I will not have a dead spot because it's coming through 0 at two different points in time. Okay, I'll never have a dead spot where both of them are in 0 at the same point. Split phase motors are used for belt drive blower applications and small appliances like washers, dryers, dishwashers, and some old furnace blowers you'll still see. I mean, very old furnace blowers. You'll still see split phase motors. Split phase motor diagram looks something like this. You'll have a run winding, you'll have a start winding, and you'll have a centrifugal switch. Okay, or some switch to take the motor to take the start winding out of the wire. One thing that I can mention here is that the run winding will always have a lower resistance than the start winding. Start winding has a long run of small gauge wire. Run winding has a shorter run of heavy gauge wire. The run winding will have a lower resistance than the start winding. And again, you can see how that here is just the left side of this is more of a pictorial diagram to see how it's all put together. The centrifugal switch removes the start winding from the motor circuit once the motor reaches around 75% of its rated speed. This is the part that most often fails when a motor is started and stopped many times. Okay, it's a movable part. It's an on-off switch. It has contacts, and eventually those contacts are going to fail. The centrifugal switch is normally closed when the motor is not operating. So your start winding is in the circuit when the motor is not operating. This is a picture of the centrifugal switch. As the motor starts to spin, it actually will open the contact that I'm circling here because the centrifugal force will pull this in the upward direction. This assembly normally fails after years of use. There's really no way to replace these. Again, this is a user non-serviceable part. It basically means you're going to replace the motor. In order to increase the starting torque, we went to adding a capacitor. We'll talk about capacitors in one of our next videos. Okay, the capacitor is in series with the start winding, and this becomes a permanent split capacitor motor, or a PSC motor. In a PSC motor, this capacitor remains in series while the motor is operating. There is no switch or relay that removes this capacitor from the circuit. Residential condenser fan motors, furnace blower motors, and compressors are the primary use of PSC motors. The PSC motors have moderate starting torque and decent or intermediate running efficiency. It's decent running efficiency. The motors are used primarily for small compressors, direct drive blower, and fan operations. This is an example of a PSC motor. Okay, and you'll see in the wiring diagram, if you look close, there's a capacitor there. This is multi-speed, so you might have high, medium, and low based on the color of the wires coming out. Any additional wires cap off and isolate. Make sure they can't short against each other. Do not put them under the same cap. CSIR motors are capacitor start induction run motors. They use a start cap and a start relay. Once the motor has reached 75% of its rated speed, the start capacitor is removed from the motor. CSIR motors have a high starting torque. In other words, they can start to move a very large load. And they're used in residential and small commercial compressors. You may see them in beverage coolers sometimes, or small reach-ins. CSCR motors, capacitor start, capacitor run motors, are the same as permanent split capacitor motors, except they also have a start capacitor wire to them. In other words, we have two capacitors. One will stay in the circuit at all times. That's the run capacitor. The other will come out of the circuit once the motor has started. Okay, a start capacitor is a high capacitance capacitor that will provide the motor with additional torque or an additional kick when starting. Once the motor is started, the start capacitor must be taken out of the circuit using a switch or a relay. These devices are called start components, and this is covered in the next section. CSCR motors can be abbreviated to CSR, capacitor start and run. Okay, so you might see it labeled CSR. It's still a CSCR. It has two capacitors, a start capacitor and a run capacitor. A wiring diagram of a CSCR motor would look something like this. From L1, we have our run winding, gets constant power while the motor's running. Start winding is taken out of the circuit, while the start capacitor is taken out of the circuit with a start switch. The run capacitor you see is in parallel with the switch, so it's going to provide the start winding with constant current. It's going to be out of phase from the run winding because that's what the capacitor does, but it's going to be a constant current. Now, Hermetic Motors deserves a little bit of its own conversation. Hermetic motors are single phase up to about 5 horsepower. Hermetic motors are those found inside the compressor shells. They're wired the same way as any other split phase motor, but the start components and all the connections are outside the compressor shell because of the refrigerant pressures. This is an example of a hermetic motor. Okay, you have run, start, and common outside the compressor. There's a seal in this area here that seals the refrigerant into the unit. It's airtight under very high pressures, and all you have access to are the 3 terminals on the outside of the compressor. Most of them are labeled someplace C, S, and R. Sometimes, over years, that labeling will wear off. Okay, this is a picture. You have a hermetic seal there. You have your common, your run, and the third has to be a start. If the windings are not marked, use your ohm meter to check the resistance. Check the resistance between all 3 windings. The 2 pins with the highest resistance are is going to be start and run. So if I have 3 pins, so I have 3 pins on the outside. If I have let's say 2.4 here, and if I have 1.2 here, actually let's change that to 0.9. And if I, between those two, if I have 1.5, the pin across from the highest resistance is going to be my common. 2.4 is my highest resistance between that and that. The pin from the across from the highest resistance is going to be my common. Then my pin from common to the next highest resistance will be my start. The lowest resistance is my run. Once you know C, check between C and the other 2 terminals. The one with the highest resistance is start. The one with the lower resistance is run, as I just showed you. The best way to write down is do a CSIR in a triangle on a piece of paper. Write down each measurement. If you have any doubt, go back and check this again. You have to isolate the compressor to do this reading. Do not do this with any wiring connected to the compressor. These readings are going to be extremely close together sometimes, and they have to be accurate. Many manufacturers publish the motor winding resistance. You just got to find it. If you compare against the manufacturer's specifications, make sure that you allow for the resistance of your meter leads. Normally, you want a plus or minus 5%. Motor speeds are shown in RPMs. RPM is revolution per minute. This is the revolution of how many times per minute the motor shaft rotates. Sometimes you need to figure out RPMs for a motor. To figure out the motor speed, first use the label and find the number of poles. Or sometimes count the number of poles. The RPM is the frequency, which in the United States is 60 hertz, times 120 divided by the number of poles. That's going to be your speed. Frequency times 120 divided by the number of poles. This is in parentheses, so you're going to do this first. And then you're going to divide it by the number of poles. This is a shaded pole diagram. This is what you're going to see on a ladder diagram. This is what we want you to draw on a ladder diagram. Label R and C. Tells everyone it's a shaded pole motor. CSCR diagram. This is a capacitor. This is my run cap. It's always in the circuit. Start cap is over here because it's protected by a switch. You have a switching device here. We know our run cap is in series with our start winding. We know that our run winding always gets uninterrupted current and voltage while the motor's running. Just because it's a run cap does not mean it's put before the run winding in series with it. Common over here may sometimes have an overload switch on it. You might see another device or some sort of protection on the common winding. Split phase diagram, again, no capacitors. Single switch to take the start winding out of the circuit. Split phase is the motor with the start winding that does not get constant current. PSC, we have a run cap wired in series with the start winding, gets constant current. ECM motors, got to touch on them. It goes past the basic electrical section, and we're going to talk about it in a separate lesson. ECM stands for electrically communicated motor. It's a combination of a DC motor and an electronic control module. They're very high-end and very efficient motors. Troubleshooting of motors falls into two sides, mechanical side and electrical side. Mechanical faults. Does the motor turn? Does the motor turn smoothly and quietly? Does the motor shaft not move in and out of the motor or side to side? If any of these answers are no, then the motor is failing mechanically. And by the way, does the motor turn? I mean, if you try to turn it manually, does it turn? Troubleshooting the electrical side, isolate the motor. Check the resistance of each winding to the motor frame. All resistances should be over 1 mega ohm. OL or infinite is better. Check the resistance winding to common. There should be resistance over 0 from each winding to common. If any winding is 0 or OL, then the motor has failed winding to winding. Smell the motor for the odor of burnt electrical. You'll know it when you smell it. It smells like melted plastic and something else combined with it, but you'll know it when you smell it. Okay, if that's happening, something is starting to burn out. Even if you haven't gotten bad resistances, there's something wrong. If the mechanical checks out and the electrical checks out, energize the motor. Take an amperage reading with it operational. If the amperage is over the motor's rated amperage, check the run capacitor and check all the wiring. If the run capacitor is good and all the wiring is good, you might have the starting of a mechanical failure as well. The bearings may be starting to fail. Make sure you're using the information to compare with from the data plate on the motor, not the data plate on the equipment. Motors may have been changed over time, and you might have different motor than what was in there originally. I've seen it happen on more than one occasion. Again, be careful with your electrical troubleshooting. Sometimes when you're taking voltage readings, you're working on energized equipment. Your hands are in high voltage. When you're taking resistance readings, protect your meters and isolate the components. Make sure the voltage is turned off. Don't just trust the disconnect or switch. Actually check and make sure the voltage is off. That's it for this presentation, and please subscribe to the channel. It's very easy to do. Click the subscribe button on the top right of your screen or right under this video, and we will see you in the next video.